Hi everyone and welcome to the video on Dijkstra's shortest path algorithm. So first let me tell you the problem. Imagine you are in one place and you want to go to many other places. So there are so many roads and every road has a distance. So the question is, what is the shortest path from the starting point to all other places? So Dijkstra's algorithm answers this question. Suppose you have a graph connected by weighted edges like this, and first we look at what are the nodes and edges and also weights. So nodes are points or entities in the graph. They represent locations, status or object. So edges are the connections between nodes and weights are numerical values assigned to each node. So they are representing the cost or distance to travel along that edge. So this can be applied, for example, in digital mapping. So suppose those nodes are cities and the edges are routes between them. So let's take a closer look at this graph, and suppose we want to calculate the shortest distance from A to every other node in this graph. So this can be easily done with Dijkstra's algorithm. We just have to keep some we just have to keep track of some information while iterating through this algorithm. So the first information we need to keep track of is which nodes we have not visited yet. So in the first step, we mark all nodes as unvisited. Therefore, we create two lists, a list with unvisited nodes and that contains every node in the graph, and also visited nodes that is empty in the beginning. In the second step, we assign all nodes a tentative distance value that will be changed over time. So therefore, we can use this table on the right, which consists of three columns. In the first column, we have the node. In the second column, we have the current shortest distance from A to this node. So beginning of the algorithm, we know nothing of any distance to any other node than A. So we set A to 0 because the distance from A to A is 0, and every other distance we set to infinity. And in the last column we store the previous node that leads us to the shortest distance, and this column will be empty at the beginning because currently we have no information about this. So those are the things we need to keep track of, and now we can start the first iteration. Since we are at the node A, we start by calculating the distance to all unvisited neighbors of A. The distance from A to B is 2 and the distance from A to C is 7. And now we can update our table on the right. If we have found a new short distance to one of the unvisited nodes, so B and C are unvisited and the current distance is infinity, so we can update the distance from A to B to B and store A as the previous node in our table. And sum applies to the node C. We can update the shortest distance to C to the value of B and the previous node A. And now our iteration ends here and we can mark A as visited. So remove it from the unvisited nodes and put it in our visited node list. The last step we didn't talk about yet is pick a new node as a current node to explore the graph further. And therefore we always choose node with the current minimal distance in our unvisited nodes. So when you look at our table, we have A with distance of 0, but it is already visited. We have B as unvisited node with the distance of 2. We have C with the distance of 7. All other nodes have distance infinity. So B has the current shortest distance of all unvisited nodes. This means that B becomes our next node. For our node B, we can now go back to our second step to calculate the distance of all unvisited neighbors of B. So unvisited neighbors of B are C and D, and the distance calculation works as follows. This B has a current distance of 2. We need to add this 2 to the weight of the edges to B and D. So now let's first look at the node B. Node D will have the current distance 8 from A over B, and now we need to check if 8 is less than the current shortest distance that we stored in our table. And the current shortest distance we stored in our table is infinity. So we update our shortest distance to D and set B as previous node. Now let's look at the node C. C will now have the distance of 7, 2 plus 5 from A over B. So this means we need to compare this 7 to our current value 8 in the table. Since our current value is less than the value in the table, it should update the previous node with the value of 7. Now we are finished with B because we visited all unvisited neighbors of B, and we can mark B itself as visited. In the next step, we choose a new current node from all unvisited nodes again, and we choose the node with the minimal distance. So the node with the minimal distance in this case is C because it has the distance of 7. So we now calculate the distance to all unvisited neighbors of C, and in this case we need to add 7 to the distance because currently the shortest distance from A to C is 7 when we look at our table. Now we need to consider if we need to update the distance to D, or we need to update the distance to E. So let's start with D. The distance from A to D over C is 10, but 7 plus 3, 10 is not less than our current distance 8 we have stored in our table. We won't update our distance to D. When we look at the node E on the other hand, the current distance we have in the table is infinity. But now we get a distance from 9 from A to E over the node C. So we update our shortest distance in the row F, set it to 9, and set the previous node to C. So now we can mark C as visited, and we can go on with the next node in the unvisited node list. And this will be D because he has the distance of 8 and he has the distance of 9 and F of infinity. So we calculate the distance from D to F and D to E. In this case we need to get 8 to the distance because 8 is the current distance from A to D. Let's start with the node F. Now we have the distance of 70 from A to F over the node D, and this is certainly less than infinity, so we can update our distance to F in our table. Set to shortest distance to 70 and the previous node to D. When we now look at E, we see that we have a new distance of 9 to C, which is exactly the same as our old distance of F. So we don't update anything. We are finished with the node D. Now we have the E and F left as unvisited nodes, and E has distance of 9 and F has distance of 70. We always start with the one with the minimal distance, so we start with E, and the only visited neighbor is F, and now we can see that we have distance of 12 from A to F if we go over the node D. So we can update the shortest distance to F to 12 to set the previous node to E and mark E as visited. So this leaves us with node F. Since F has no unvisited neighbors, we are done here, and we can mark f has finished, and now we are done with the algorithm. And in our table we have some important information about this graph. So we have now the shortest distance from to every other node in this graph, and we have the previous node which helps to reconstruct the shortest path.